Hi students. In this lecture, I am going to discuss problems based on impulse and collisions. Let us see first one. Right, see the question. A wooden log of mass capital and length L is hinged by a frictionless nail at O. A bullet of mass M strikes with velocity V and sticks to it. Find the angular velocity of the system immediately after the collision about O. So given it is a log, or you can say uniform rod, mass given, length given, it is now hinged at one end. Given frictionless, a bullet of mass m strikes with a velocity v and sticks to it. So we have to find omega for system immediately after the collision. So asked for 2 marks in 2005. Let us see how to start. So first of all, make the diagram given. So it is now fixed at one end, that is point O at one end, about which we have to calculate angular velocity for system. It's a mass m, length is L. Now a particle of mass small m, it has velocity v, strikes at the other end and sticks to that. Okay. So we have to find omega value. So here we can see, since one end is fixed, rotation will be about same axis. That means we have to conserve angular momentum about same axis. Or we can take like this. Suppose it is in a horizontal plane. If it is in a horizontal plane, say forces acting on the system on this rod mg downwards, normal reaction upwards, and these two are passing through center of mass of the rod, right? And these two are cancelled. Coming to for particle, again its weight mg downwards, normal reaction upwards, and these two are cancelled. Now we can see about point O torque equation. On the rod mg downwards, normal reaction upwards. Torque due to weight of the rod and torque due to normal reaction both will be opposite and having same values. That means both will cancel each other. Now same thing happens for particle also. mg downwards, normal reaction upwards. That means if we are taking about this axis of rotation, net torque on the system, that means rod and particle system, is 0. That means we can conserve angular momentum of the system. Okay. Because here at the point of suspension, there may be a hinge reaction. Okay. But since we are taking about the point O, because of those hinge reactions, the torque will be 0. Right. So we are taking now law of conservation of angular momentum. It is about point. So only key point is that about which axis body rotates, about same axis we conserve angular momentum. Okay. Now see here, m into v into L, because about point O, right? That is before collision. Coming to after collision, now this sticks to the other end. Now we can see I value, I into omega. I am writing here I into omega. And coming to I value for the rod about 1 in ml square by 3 per particle ml square. This is I value into omega, right? So from this, we are going to get the value of omega. It is a very simple and direct one. Okay. Now do one thing. For example, this rod is not fixed. So we are taking now this entire system on a smooth surface which is horizontal. This entire one. We assume that rod is not fixed. Okay. Then say possibilities when rod is not fixed. One possibility is that particle sticks to the rod. Okay. So I'm taking here one possibility. Particle sticks to the rod. So here we are taking the condition rod is not fixed. And one possibility rod not fixed and a particle sticks to the rod after collision. Okay. When it sticks to the rod, then system rotates about the common center of mass. Suppose this is now center of the rod. Okay. When particle sticks to the rod after collision, then rotation will be about the common center of mass. It is not about center of the rod. Okay. We can see center of mass for rod and particle system. It will be somewhere here. That is now center of mass of the rod particle system. So if particle sticks to the rod, then rotation will be about the common center of mass. Then we have to conserve angular momentum about the same axis. Okay. Next, the second possibility, particle is not sticking to the rod. Okay. If it is not sticking to the rod, then what happens is rod rotates about its own axis. That means through center of mass of the rod. See carefully. So rotation will be about this axis. If particle does not stick, if particle does not stick, then rod rotates about center of the rod if rod is uniform. In this case, what happened? Sticks to the rod. Then rotation will be about center of mass of the rod particle system. So here we conserve angular momentum about this common center of mass. Coming to here, we conserve angular momentum about center of mass of the rod. So here common point is that about which axis rod rotates. About the same axis we conserve angular momentum. See here, it is a fixed. So about point O, we are conserving angular momentum. Here, sticks to the rod. About common center of mass, it is rotating. About same axis we conserve angular momentum. Coming to here, does not stick. Rod rotates about center of mass of the rod. So we conserve about center of mass of the rod. So in these three cases, common point is we conserve angular momentum about which axis a body rotates. Okay. So I hope you got the clarity. Let us go for next question. See the question given. A uniform rod of mass m, a length L, is struck at an end by a force F perpendicular to the rod for a short time interval t. Calculate the speed of the center of mass, the angular speed of the rod about center of mass, the kinetic energy of the rod, and the angular momentum of the rod about center of mass after the force has stopped to act. Assume that t is so small that rod does not appreciably change its direction while the force acts. Okay, so it is a uniform rod applying a force for a short time interval at one end. Let us see. Take the system on a smooth surface which is horizontal. So it is given rod mass. It is m, length is l. Applying a force F for a short time interval at one end. It is normal to rod length for a short time interval. See, its meaning is an impulse is given to the rod. Okay, a force F acts for a short time interval. Its meaning is it is just like an impulse is given. How much impulse means? Impulse that is equal to J equal to F into T. Right? Okay, now see carefully. First one, speed of center of mass. So here one thing we have to focus very carefully. If a force is passing through center of mass of the rod, then rod is having only translatory motion. Rod is having only translatory motion. If force is not passing through center of mass, then rod is having translatory motion as well as rotation about its center of mass. Since rod is uniform, it is about center of the rod. Okay. Now see what we can write. An impulse J is given. Impulse equal to change in momentum. So we are taking for center of mass impulse F into T, which is equal to change in momentum. That means mass into final velocity. So I'm taking VCM minus 0. Okay. So from this we get VCM. So velocity of center of mass. So directly we can say it is Ft by M. Okay. Next, see what we have to calculate. The angular speed of the rod about center of mass. Angular speed. So when we apply force about at one end, rotation will be about center of mass of the rod. So just now we have discussed, we conserve angular momentum about which body rotates. Okay, so it is now taking LCAM, law of conservation of angular momentum. So it is F into T, that is impulse. Rotation is now about center of the rod. So distance will be L by 2. So Ft into L by 2. This is now angular momentum. That is equal to I omega. I value ml square by 12, right? Into omega. Then see what is omega value. L gets cancelled here 6 times. That means we are going to get omega equal to 6 Ft 6 Ft upon ml. 6 Ft upon ml. Okay. Right. Now see what we have to calculate. Next one. Right. It is speed of center of mass over omega is over. Now kinetic energy of the rod. So we have to get the kinetic energy of the rod. So it is having translation and rotation, right? Because the force is not passing through center of mass. That's why having rotation plus translation. You can see since the force is now, it is the right side. Rotation will be, it is anti-clockwise and center of mass velocity like this. So it is now rotation plus translation. Okay. So calculate now kinetic energy because of rotation and because of translation. Okay. It is equal to half m v square, that is vcm square. So ft by m. This is the kinetic energy of the rod because of translation, half m vcm square, plus because of rotation, half 5 omega square, and I value ml square by 12, half 5 omega square, and omega value 6 ft by ml. Okay. Now remain just calculation part. Half I omega square. Okay. Right. 6 square 36. This is 12. 3 times. So 3 by 2. 3 by 2. 1 by 2. That is 2. Remaining is now see carefully. F square T square. You can take it outside. F square T square. You can take it outside. What else left? M square and M. One M is left here. Here. L square. L square. It is over. M square. Sorry, it's only M, right? M L square. M square. And one M is here we have taken. It is now answer is 2F square T square by ML. Right? Wait. It is anything missing here. Ft equal to M into VCM. So Ft by M. Right? So here L square cancelled is only 2 F square T square by M. Okay. Next. So next what we have to calculate. So coming to D, angular momentum of the rod. Angular momentum of the rod. It's about which axis? Angular momentum of the rod about center of mass. After force has stopped. So it is equal to, directly we can write I into omega. Right? Because he's asking now about center of mass. About center of mass means because of translation, there is no angular momentum. I am writing here. Angular momentum about a point is equal to, because of translation, r bar cross p bar, because of rotation, I omega bar. Okay. So here we are taking about center of mass. Then r bar and p bar are in the same direction. Okay. That means between these two vectors, angle is 0. Next, the remaining is only rotation about center of mass. So directly I value ml square by 12. Okay. Omega value 6 ft by ml. Right. So like this we can calculate. Okay. Let us see next problem. Let's see the question given. Consider a body shown in figure consisting of two identical balls, each of mass capital, connected by a light rigid rod. The rod has no mass. Given light, an impulse J equal to mv is imparted to the body at one of its ends. Its angular velocity would be. You can see this question is almost same as the previous problem. In previous problem, it was given rod. It is now here light rod having two particles. Okay. So question almost the same. Now see, we have to find omega, how to calculate. Given massless rod having 2 point masses m and m. Now we are giving an impulse. So giving an impulse. So masses are same, m and m. Rod length is L and rod has no mass. An impulse J, which is equal to m into b, is given. See now what happens. When an impulse is given, now for this rod, rotation will be about center of mass. Since both have same masses, center of mass will be center of the rod. Okay. So rotation will be now, it is anti-clockwise. Now see calculation. It is m into v into L by 2. Means I am writing J into L by 2. Okay. This is J. J into L by 2. That is now angular momentum about center of the rod. That is equal to I into omega. Now see what is I value? M square of L by 2. This is for 1 point mass. Same thing for other one into 2. Okay, this is I into omega. Okay, now simplify this. It is just matter of one single step. M cancelled. 2, 2, and 2 gets cancelled. And 1 L gets cancelled. Remaining is now omega equal to, it is V upon L, right? So almost same as the previous problem. Even in this also, we can calculate kinetic energy of the rod. Okay. Let us see next problem. See the question given. A uniform rod of mass m and length L is placed on a smooth horizontal surface whose one end is fixed. A force is applied normal to the rod at a distance x from the fixed end so that hinge reaction is zero just after applying the force. Find the value of x. Let us see. Let us make a diagram for the given data. Given a uniform rod fixed at one end, and this is placed on a smooth surface which is horizontal. We can say mass is m, length is L, and a force is applied normal to the rod at some distance x. Condition is that for what value of x, hinge reaction will be zero, right? Now see how to start the problem. So since the rod is fixed, rotation will be about the fixed end, right? And if you observe, center of the rod that follows now circular path. right? So when force is applied, now this will be along the tangent. This is now along the tangent, right? We have to find just after applying the force, there is no hinge reaction. Just after applying, then see what happens here. Center of mass is having acceleration, which is now along the tangent because it follows now circular path. This is now tangent. That means acceleration of center of mass, it is now tangential acceleration, which is equal to r into alpha. And r will be L by 2. L by 2 alpha. Okay. Then see what we can write here. I can write here net force is applied force. Why net force equal to applied force? Because there is no hinge reaction. See carefully. It is on a smooth surface which is horizontal. mg downwards, normal reaction upwards. These two are balanced. Applying force here. Condition given no hinge reaction. That means applied force is net force. Net force equal to mass into acceleration. And acceleration is r alpha. Right? Now to find alpha, we have to take torque equation. Since rod rotates about a fixed end, take torque about same axis. That is F into L by 2. That is equal to I into alpha. I value ml square by 3. Rotation about one end of the rod, right? I alpha. Then see calculation part, which we can cancel here. L cancelled, 1L. From this alpha equal to 3F by 2ml. Now take that in this one. F equal to m into L by 2 in the place of alpha, 3F by 2ml. Cross check once. Is it okay? 3F by 2ml. Now simplify this. Mass cancelled, L cancelled. Wait. I made a mistake here. This is applied not at center of mass, okay? Condition is given that applied at a distance Ex, right? And this also not correct. Applying force at some distance X. At some distance X, it is F into X. Okay. Then this becomes now 3Fx by F2 is not there. Or let us calculate once again this and this also. Right. So alpha equal to F into X equal to I into alpha. Alpha equal to 3Fx by ml square. Now substitute that in this m into L by 2 in the place of alpha, 3Fx upon ml square, right? Now see calculation part. F cancelled, m cancelled, one L is cancelled here. What else left here? X equal to 2L upon 3, 2L by 3. Means if a force is applied at a distance 2L by 3 from the fixed end, there is no hinge reaction. Or we can say, if an impulse is given at some distance x, There is no impulse because of the hinge, and that point is known as center of percussion. That point is known as center of percussion. Okay, that is 2L by 3. Okay, so I hope you got the clarity.